Hi, in this session, we'll be discussing regarding vapor compression system and especially we'll be discussing regarding the problem related to wet compression. So we have already discussed the working of a vapor compression system with our major components being evaporator, compressor, condenser and expansion valve. In our vapor compression system with wet compression, the only difference from the ideal system is that the vapor entering or the refrigerant entering the condenser will be a wet vapor. That is, it will be a combination of liquid and vapor refrigerant, and it will not be a saturated vapor as we have seen in our previous ideal vapor compression system problems. The point one actually lied on the saturated vapor line, but here actually this will be inside the dome. Also, there will be two type of wet compression, namely one is actually the vapor after compression in our compressor will also be a wet vapor, and the second condition being vapor after compression becomes a saturated vapor. Now, this will be specifically specified in the question. If it is a saturated vapor, it will be specified in the question. If it is not, we have to find the enthalpies of the points 1 and 2 using the concept of dryness fraction. There won't be any change in COP. That will be nothing but refrigerating effect H1 minus H4 divided by work done. It will be H2 minus H1. Then the important relations which are same actually, the refrigerating effect also will be same. The actual difference of formula actually comes here where we may need to evaluate the properties or enthalpies at points 1 and 2 respectively using these three formulas, where H1 is mainly given by HF, enthalpy of fluid corresponding to the evaporator temperature, plus X1 being the dryness fraction of the vapor refrigerant or liquid refrigerant entering the compressor, into HFG, latent heat of vaporization at the evaporator temperature. Similarly, H2 will be nothing but our HF, enthalpy of fluid at condenser temperature, plus X2, the dryness fraction of state 2 into HFG, that is nothing but the latent heat corresponding to the condenser temperature. Maybe the value of X2, that is the dryness fraction at state 2, may not be given. That we have to find out using the formula, that is entropy at S1 is equal to SF plus X1 into SFG, where SF is the enthalpy of fluid corresponding to the evaporator temperature, X1 is the dryness fraction of state 1, and SFG is the difference in the enthalpies of gas and fluid at evaporator temperature. And using the concept S1 is equal to S2, we can find the value of S2 and substitute it back into this equation for finding the dryness fraction at state 2, which will be discussed in the later session. Now, coming to the problem, we have determined the theoretical COP of a vapor compression refrigerator with carbon dioxide as a refrigerant working between the temperature limits of 25 degrees Celsius and minus 5 degrees Celsius. The dryness fraction of carbon dioxide at compressor section, that is at point 1, is 0.6. So here, nothing is specified about the state of the vapor after compression. So we'll assume the point 2 as well as point 1 is lying inside our dome or chart, that is both are wet vapors, that is a combination of liquid and vapor refrigerant, since nothing is specified about the state 2 or the state of the refrigerant after compression. Now the given values or data mainly includes the evaporator temperature, which is at minus 5 degrees Celsius or 268 Kelvin. Similarly, the condenser temperature 25 degrees Celsius or 298 Kelvin. Also the dryness fraction at compressor suction, that is X1 being 0.6. As we had discussed earlier, since this location of point 2 inside the curve is not known, so we have to find out the dryness fraction of state 2. Also, since the data is not given, we cannot assume the point 2 is actually lying on the saturated vapor line. Also, it is better to do this problem using this analytical methods, that is using charts rather than the graphical method. So we'll be actually taking the values of the refrigerant 744 at temperatures -5 and 25, the values being Vg, Hf, Hfg, Hg, Sf, Sfg and Sg respectively. Also, first of all, we had to calculate the enthalpies at points 1, 2, 3 and 4. So initially, we know the enthalpy at 1 is nothing but enthalpy of fluid at -5, which is 72.57, plus x1, that is the dryness fraction at point 1, which is 0.6 rather, into latent heat at corresponding to evaporator temperature. That is nothing but HFG at -5, 248.76, which upon calculation gives the value to be around 221.83. Similarly, H3 can be thought of as we had discussed earlier, only 1 and 2 is actually lying inside the curve or dome. The point 3, that is the condition of the refrigerant coming out of the condenser, will be a saturated liquid. So 3 will be nothing but the enthalpy of fluid. H3 will be nothing but the enthalpy of fluid corresponding to the condenser temperature or 25 degrees Celsius. That will be 164.77 kilojoules per kilograms. Similarly, H4 will be equal to H3 as 164.77 kilojoules per kilogram. Now, we need to find the enthalpy at point 2. So for that, we need to find the dryness fraction at 2, that is H2. Then we need to find the enthalpy H2 using the respective formula. So first of all, we know the enthalpy at S1 can be found out by enthalpy of fluid at -5 degrees Celsius, that is 0.2862, plus x1, that is dryness fraction of 0.1, 0.6, into the enthalpy difference of gas and vapor SFG at -5 degrees Celsius, which is 0.9824, which gives enthalpy at point 1 to be 0.8432 kilojoules per kilogram Kelvin. Also, we know the enthalpy at 2 will be same as enthalpy at 1, that is in compression is isentropic in nature, constant entropy. So enthalpy at 2 can be written as 0.8432 kilojoules per Kelvin, and this enthalpy at 2 can be rewritten as enthalpy of fluid corresponding to the 2 is actually in condenser temperature, so 25 degrees Celsius plus H2, that is the dryness fraction of 2 we need to find out, into our SFG corresponding to 25 degrees Celsius, where the values of SF and SFG we have already made it into a table. So by substituting the values for as 0.5978 as SF and 0.3940 at SFG, which is equal to 0.8432, we can easily find the value of dryness fraction of our point 2 or state 2 as 0.63. Similarly, and now we can find the enthalpy of H2 as HFH 25 plus X2 into HFG at 25, which is nothing but 164 plus 0.62 into 117.46, which actually gives the value to be around 238.77 kilojoules per kilogram. So we have got the enthalpies at all points 1, 2, 3 and 4. That is, we have got H1 to be 221, similarly H2 to be 238, also H3 to be and H4 to be 164.77 kilojoules per kilogram. Now, the question was to find the COP, which is nothing but the refrigerating effect by work done, or simply H1 minus H4 by H2 minus H1, which upon substituting the values, we'll get the COP to be around 3.37.